Hello and welcome back for another lecture. This one is on the reasons for the seasons. We'll introduce the solstices and the equinoxes and discuss energy distribution of sun on our planet and length of daylight. So it's often concerned as to what are the reasons for our seasons, and we'll learn that it's not just one answer, that there's a lot of attributes that allow for our seasons to occur. Now, that being said, living in Southern California, our vision of seasons is hot, not so hot, kind of hot, and warm. We don't really have a large fluctuation. And as we'll learn today, that has a lot to do with our latitude and where we're located on the globe. Now, places just a little bit farther north than us do experience seasons. In fact, this photo here that I'm sharing, this is of one of my favorite places along the eastern Sierra. This is Lake Sabrina in Bishop, California. And based on their altitude and latitude, they do experience a lot of that seasonal change. They see the fall colors, usually the first week of October. They last all the way through the month, and you can see the transition of colors. So if you ever get a chance to head up there during that time of year, you'll really get an opportunity to see what fall is about. Otherwise, again, living here in Southern California, fall usually lasts for one day. The leaves turn orange-brown, they fall off the next day. So that has a lot to do with our weather climate and our line of latitude. So let's start off with this. So as discussed in other presentations, we have uneven and unequal heating on our Earth's surface. That energy that is of unequal provides really the fuel for our weather systems. But when kind of taking weather out of it, knowing that the distribution of sunlight is not equal on our planet will start to paint the picture as to, oh, well, that's one of the reasons why we experience seasons. So as we can see, nearly all the energy that drives Earth's weather comes directly from the sun. The energy is not distributed evenly, and as a result of this, the imbalance will drive oceanic currents and surface winds. Now, the Earth is tilted at 23.5 degrees from the vertical. So what does that mean? So here's a little animation I found, which I thought was kind of neat. So this is obviously representing the Earth and putting it in perspective. So there the Earth is, rotating counterclockwise. We can see that because of this tilt in particular, that at this exact moment where the Earth is being tilted and its rotation, that you can see that the northern hemisphere is tilted more towards the left, the southern hemisphere is tilted more towards the right. So depending on where you are, and where we're viewing this, that can really give us a lot of information about intensity and duration. So let's first kind of introduce those concepts of intensity and duration. So I found this image. I thought this was super neat. This was an old book from the 1950s, but I think it does a great job trying to visualize the differences between intensity. So intensity is the measurable amount of energy given to an area. So here we have an example. We have two globes, one on the top, one on the bottom. And if you notice, the guy is holding a flashlight and this piece of cardboard, and that piece of cardboard has a perfect equilateral square cut within it. So he's first in the top image, he has the piece of paper with the flashlight and then the globe, and you can see it's a straight shot, right? So the size of that square is going to be the exact same size on the globe itself that's being illuminated, right? Well, that's because everything is perpendicular. In that case, all the energy coming from that flashlight that's passing through that cardboard is all concentrated on the exact same size square. Now, looking at the diagram below, as you see, everything is the same except that you can see that the square is a different shape that's being illuminated. The square in the cardboard is the same cardboard, but why is it a different shape? And the reality is because if you notice on that bottom globe that there's a curve to the Earth. And so now that once perfect square is now being stretched. That light is being stretched over a larger surface, which therefore decreases the intensity. So if that almost makes sense, maybe not quite, think about just like a movie projector, in a classroom or at home. It's very depending on how that screen and the angle in which that projector is being, showing its light will affect the image, right? So you probably have seen where the screens moved or the projector's tilted and it stretches and skews the image, right? You know that the more perpendicular and straight on that movie projector is and the closer it is, the clearer the image. The farther away you are, sure, the film will be on a larger screen, but it's not as clear, not as bright. And that really is kind of that definition of intensity, as well, how much energy is within that given area. So we find that when light is perpendicular onto a surface, it's most intense, right? This, you guys can't see, I got one of these things. I bought it at the store so it looked more professional. But if the light is straight on my face, it's a lot more intense versus when I have it at an angle. It's still the same amount of light, but now it's being covered over a larger surface. So that kind of changes that. And then the last part here is duration. For how long? Do we have 12 hours of daylight? Do we have 6 hours of daylight? Do we have 24 hours of daylight? So there's a great variation of daylight, and we'll see that a little bit later in a table. And it's kind of hard for us to sometimes imagine that there are places on this planet that get 24 hours of daylight and 24 hours of darkness. So let's kind of put this together. Obviously, not to scale. Here we have our sun, here we have our Earth, here it is at its tilt, where we talked about that. So what's interesting is this word incident, these incident rays. So what we see is at this point, doesn't matter the season, doesn't matter the time of year, at this exact moment of representation, here we have the Earth. We're located somewhere up here. Look at how short our length of daylight is versus someone, say, living right here. Look at how long or how much of the globe is exposed for daylight there. Well, if you kind of use deductive reasoning, you'd be like, well, because of the tilt of the Earth, and as you can see, there's this line is called the circle of illumination. We can see that more of the northern hemisphere is experiencing darkness, more of the southern hemisphere is receiving daylight. Just on that alone, you should be able to deduct that this must be when we experience winter in the northern hemisphere, and this is when we experience summer in the southern hemisphere. So what we find is during this time of year, the most intense radiation being absorbed on the Earth, the region that is perpendicular, the most intense amount of energy is actually the Tropic of Capricorn, right about down here. Right, this line right here represents that perfect perpendicular, going back to that previous slide, that little cardboard piece with the perfect square. That is where that perfect square will be. It's the most intense amount of energy. And then as we get farther away from that line of latitude, we observe that there now is an angle, which means that light is being stretched and it's not going to be as strong because it's covering a larger area. In fact, if you think about it, if this was a top, the Earth, and we could spin it in this image, you would recognize that this zone right here, it doesn't matter how many times you are just spinning the Earth, it will never have darkness. These people here, between this latitude to the South Pole, 24 hours of daylight. What about up here? Same thing. Everyone up here, 24 hours of darkness. Crazy, right? So you might be thinking, oh, well, perfect. So it's just intensity. No, it's also going to be duration. That's the reasons for our seasons. Okay, so moving forward, I found this little animation. I'm going to stop it along the way. I just thought it was kind of interesting. So this is showing first the Earth before a tilt. Then it puts it in perspective that the Earth is tilted in relationship to the sun. So I think I can pause it right there. So we can see this is your circle of illumination. At this point in this projection, we can see that the northern hemisphere is still experiencing winter. The southern hemisphere is experiencing its summer. So I'll hit play. And notice what happens as it spins around. So I'll pause it there. So we can see this is winter. Look about, just, again, the Earth rotates, right, counterclockwise. So if this were to spin around, if we live right about here on this line, look at how little of daylight hours will have versus how much more darkness. Think about winter, right? Think about the length of daylight. Do we have longer days or do we have longer nights? And during the winter, you know that we have longer nights, right? We have shorter length of day. And then we hit play again. Watch this guy move around a little bit more. Here's 6 months later, so now it's going to change direction. So, looking in a heliocentric model where the sun is somewhat offset into the middle of all of this. Now the Earth has come all the way around to a different side of the sun, so we went halfway around our year. We can see that now the northern hemisphere is tilted towards the sun. The southern hemisphere is tilted away. So here we're experiencing our summer, and there we experience our winter. We hit play again just so you can kind of get an example of how that spins and rotates. And then comets have seasons too, but we don't care. Well, we do care, but not right now, not this moment. So here is a diagram. I could not find a clearer image, so I do apologize, but this kind of gives us an example of looking at length of daylight. So in this particular diagram, look at how the Earth is tilted in relationship to where the sun would be. Is northern hemisphere, where we live, experiencing winter or summer? It's summer. So hopefully you guessed it. I imagine you said it out loud when I asked that. So that being said, we see the northern hemisphere is tilted towards. So look at it, everyone that lives up here. Ignore these degrees for now, because these degrees are not latitude degrees. These are degrees in which are receiving of the sun. So this is where the sun's rays are perpendicular. That's what 90 degrees means. This is the Tropic of Cancer right here. So we can see that everyone above this blue line is 24 hours of daylight. Everyone down here, 24 hours of darkness. So if we live about 34 degrees north, we're just right about along this line here. So during the summer, we're looking at somewhere between 14 or so hours of daylight during the summer, which means the balance, the difference, would be of darkness, right? So what they're showing is just different lines of latitude at this particular tilt. How many hours of daylight do they have? Now these angles here, again, do not represent the line of latitude, but represent the angle in which the sun's rays are hitting, those incipient angles in which the sun is hitting the surface of the Earth. So the areas that are perpendicular receive the most intense, and then as we get farther away, as you decrease that angle, you also decrease the intensity. So that's what that's representing. So again, this red line, in case you haven't put it together yet, that equals the equator. The equator is kind of boring in this sense. There's very, very little change. They pretty much have a mild summer all year round. They never really change for their seasons. It's very, very, very slight. The top line here, this is the Tropic of Cancer. So the Tropic of Cancer is receiving the most intense radiation during summer for the northern hemisphere. This down here, this blue line here, this is the Tropic of Capricorn. That would be a 90 degree during their summer, but since it's their winter, it's down here. Then we have the Arctic Circle up here and the Antarctic Circle down here. So we have these very special lines of latitude. So I have a video shared on Canvas. It's a TED Ed video. It's fantastic. It also explains the seasons. I highly suggest that you watch that. We're not going to watch it here because it's kind of redundant. It's kind of to watch a movie in a movie. It's a little bit much. But we'll go down here to this diagram. So we have these things called solstices and equinoxes. So we'll start with a solstice. A solstice is when either pole is pointed more directly towards the sun. So that would be their summer, right? So we have the summer and then the winter. So, if it's the summer solstice, that means that your hemisphere is tilted towards the sun. If it's your winter solstice, that means your hemisphere is tilted away from the sun. An equinox is equal, meaning that everything is equal. The sun's rays are perpendicular at the equator. You receive equal amounts of daylight and darkness. So you have 12-hour days, 12-hour nights. Everything is equal equinox. So again, diagram from the 1950s. I thought it was kind of cliche, but I love it. So as we can see, this diagram here will start here. This is representing spring, the spring equinox. So spring, and you have flowers. Another word for the spring equinox is vernal, the vernal equinox. So we can see that the circle of illumination passes through the North and the South Pole. The globe is 50% exactly cut that way. Daylight, nighttime. It's always that way, but this time we're looking at it from North Pole to South Pole. That's where that line is drawn. So everyone receives equal amounts of daylight and equal amounts of darkness, no matter where you live on the globe. Now, this is, we'll get here in a moment, this is fall. You see it's completely dark. Well, that's just because that's this side. The other side is facing the sun, so that's lit up, but we'll go anyway. We'll start here. So this is the spring or the vernal equinox. Then we move into our next season. Well, what season is next? Well, here's a little guy swimming here. So it must be summer. The northern hemisphere is tilted towards the sun. The southern hemisphere is tilted away. We are experiencing summer. They're experiencing winter. Then we transition again, 3 more months out of the year. Here we go into fall, or the autumnal equinox. So this is again, these are very similar in style. Because when you think about the equinoxes, what's interesting, I'll talk about that in a moment, but I think of them as transition zones, and I'll explain that in a moment. Then we move 3 more months out of the year, and we get into what? Winter. Look, guys skiing. Here we have the northern hemisphere is tilted away, so that's our winter. The southern hemisphere is tilted towards the sun, it's their summer, and then we move again 3 more months, and we move back into spring. So if you think about it, these are your extremes, right? Your solstices are the extremes, and these are kind of your buffer zones. So you're going from cold to hot, so you're transitioning, so you're actually slowly warming up to this, and then you're going from hot to cold, and then you use this equinox to slowly cool it down and work its way across. So this is essentially our seasons in a diagram. Now, when you think about the dates in which we have, they're broken up into 3-month intervals. So what would be the month that we experience spring? It's in March. Then we move 3 more months, March, April, May, into June, July, August, September, October, November, December, and that is our calendar year. Now, what about the particular dates? Thanks for asking. Well, here we go. These are the characteristics and the dates. So we can see that the summer solstice, this is all for the northern hemisphere, June 21st through the 22nd, it's within that transition zone. That's the summer solstice, the winter solstice, and then the equinoxes. This is dealing the vertical rays of the sun, that is the latitude that is receiving the most intense radiation. Talking about then the length of daylight. So this is during the summers when we have the longest day versus the shortest day. Everything's equal over here. And then the angle of the noon sun. So what is the noon sun? Well, there's a difference between solar noon and this type of noon. This is agreed upon. This is a standard unit. So solar noon is the highest the sun is in our viewpoint at the zenith, the highest point that it ever reaches. So that's what that means. So at the angle of the noon sun, it's at its highest point, which means that if you live, it's kind of interesting, if you live at 23.5 degrees north, the angle noon sun is so perfectly above you because you're perpendicular to those rays, you wouldn't have a shadow. Your shadow would be completely at your feet. Now, we don't live there. We live 34 degrees north. So even on our longest day, you have a very small shadow. But think about it, right? Throughout the course of the year, if the sun is more above you, you have less of a shadow. If the sun's more at an angle into your viewpoint, then that shadow gets lengthened, right? So anyway, I just thought this was a very easy diagram to understand, so I hope that that helps a little bit. So there it is, right? You're thinking, okay, so it's intensity, duration, there's our seasons, easy peasy. Well, almost. One more thing. We have the perihelion and the aphelion. I've also heard it pronounced aphelion, but I like perihelion and aphelion. It doesn't really matter. It's not tomato, tomato, right? So as you can see here, we have a small onion and a olive with a pimento in it. And this diagram is representing, obviously very distorted, the perihelion and aphelion. There is actually a time when we're 5 million kilometers closer and farther away from the sun throughout the different times of the year. So what's interesting is in January, we are about 147 million kilometers from the sun. In July, we're about 152. So July, we're farthest from the sun. Okay. Now think about that. We are closest to the sun in January. What season do we experience? It's winter. But we're farther away from the sun in July. And what season do we experience? Summer. Now you're kind of like, I don't get it, right? That's kind of weird. Well, the big thing is, yes, we are closer. So obviously, if you're closer to the source of energy, it's more intense. Yes. But the kicker is we have, even though we are closer to the sun in January, our length of daylight is less, right? So we have much longer hours to cool off. That's the catch, the caveat, as he would say, right? And the same thing here in July. Yes, we are farther, but we have longer days. So since we have longer days, we have more time to absorb that energy and less time at night to release it. That's the kicker. So what I'll do is I'll hit a little button here, play so you can watch it. What's interesting about this is when the Earth is closer to the sun, notice how much faster it gets, right? That's because of gravity. And then when it gets thrown out, it slows out a little bit. So this actually makes a difference if you think about it, right? So putting this in perspective, think about just your average day. During the summer, the sun, in our perspective, it rises and it sets. In the summer, it goes really high up into the sky and comes all the way down, right? But during the winter, it kind of comes up right about here and then sets down, right? The higher the sun is in your viewpoint, the longer your length of day. The lower it is, the shorter your length of day. Okay, so that plays a role into it. We can see that this speed, we'll talk about why this speed makes a difference in a moment. And we can see that the distance between the Earth and the sun plays a moment and an effect on this. So does intensity and duration. So the reason for the season is not just one answer. It's a whole big piece. Anyway, I thought that was kind of interesting. So are there any patterns that can be observed with this? Yes. So, as I said already, you already know that during the course of the year, you know that during the summer, the sun goes much higher in the sky and comes back down for our viewpoint. Obviously, the sun's not moving, it's us. During the winter, we have a lot less, so it rises and sets, a lot closer to the horizon. Well, if you put a camera on your building and you stuck it up, and you took a photo every Monday at solar noon when the sun is at its highest point in the sky, what image would you get? You would actually get an analemma. An analemma is the chart of the position of the sun at solar noon at fixed points throughout the year. So if you Google analemma, you'll see all kinds of cool photos that show what it looks like. One of my this probably will become pointless at some point, but there was a great movie. It was called Castaway, and it had Tom Hanks in it. And if you Google analemma and Castaway, he drew one on the wall, and then you'll remember it because then, if you remember the movie, he was on an island. Spoiler alert. And he didn't know how, he knew exactly how long he'd been there. He was able to track the tides. He was able to understand everything because he was using the angle of the sun and the sunlight that would come through this cave and light up the wall. So he knew exactly how long he was. He was able to draw a calendar. So what we see is, if, as an example, let's say today's date is March the 10th. Well, March is here. There's the 10th. If I go across here, that means March the 10th, someone who's living at about 4.5 degrees south of the equator, they're going to be receiving solar noon, a point in which they will not have a shadow. The sun will be perfectly above them. In fact, if you start looking at this diagram, it's a calendar. And if you notice, we're looking at 23.5 degrees south, 23.5 degrees north. It's like, wait a minute, those are our tropics. Here's the equator along the middle. So you're actually able to pinpoint a particular date and a particular line of latitude in which the sun would be giving its most intense radiation, or their longest day of year, right? Now, what's interesting about this, you might go, well, wait a minute. Well, why isn't it a perfect figure eight? Why is it smaller in the top and bigger on the bottom? Great question. That brings us back to this. Notice that June's on the top, December's on the bottom. What happened in here, right? Remember how I told you how it speeds up and slows down? Well, that speed difference is replicated here on the analemma. Now, I kind of photo cropped it so you can't see it. There's usually some additional numbers on top of the analemma that help you measure the speed in which the Earth is traveling within its orbit around the sun. So there's certain times that it goes faster and slower. Is it important? Well, of course it is. That's kind of like our survival of a planet and how we work, but not for necessarily at this level. At this level is just more of understanding. Oh, okay, I get it. We have a chart that we can use, that we can plot, particular lines of latitude with their declination in relationship to the sun and who is receiving the most intense radiation at that time of year. All right, so there is that. Um, a lot of information, I know, but I hope nonetheless it helped answer some questions. Again, there's some great resources on TED Ed that I've shared within the modules that will help you kind of explain the seasons again, and viewing a couple different animations. But nonetheless, what are the reasons for the seasons, the solstices, and the equinoxes? Well, we're looking at the tilt of the Earth. We're looking at the length of daylight. We're looking at the intensity of that energy, the duration of the light. We're looking at the distance of the Earth from the sun. So again, there's not just one answer. There's lots of different elements that help shape the seasons that we experience. So as the seasons change, so will we. I look forward to seeing you soon, and we'll talk then.